This video we shall be discussing about the crystal field theory, or we call it as CFT. Okay. Now, in crystal field theory, it was developed by H. Bethe and Y. Black. Here, when we compare to valence bond theory, crystal field theory has more advanced and satisfactory explanation regarding bonding and the properties of the coordination compounds. In case of valence bond theory, the bonding between the metal ion and the ligands were purely considered as covalent, whereas here in crystal field theory, the metal ligand bond arises from the electrostatic interaction between the metal ion and the ligands. Okay, so the ligands are treated as point charges. Suppose if the bonding is between a metal ion and the ligand which has a negatively charged ion, it is called ion-ion, or it arises due to the ion-ion interaction. Okay, and if it is between, or if the bond is between metal ion and a neutral ligand, then it is called ion dipole interaction. Okay, now in case of any free metal, okay, here in crystal field theory we shall mainly deal with the d orbitals. Okay, in d orbitals there are 5 orbitals, and all these 5 orbitals are of the same energy. Okay, they have different shapes. Okay, and all these 5 orbitals have same energy, therefore they are called degenerate orbitals. Okay, for a free metal ion. But if any ligand approaches towards the central metal ion, okay, then when the ligand approaches, the electrons present in each of the orbitals, okay, present in each of the orbitals, especially dealing with the d orbitals, if okay, the ligand is at an equal distance from each of the orbital. Okay, if all the ligands are at an equal distance from the orbitals, that is d orbitals, from all the 5 d orbitals, then they are repelled by equal energy or same energy. Okay, but then when we see the orientation of all the 5 d orbitals, they do not have the same orientation. Okay, and therefore the energy will not be same when the ligand approaches. Okay, because the d orbitals are of not the same orientation, therefore there will be an energy difference in all the d orbitals. So crystal field theory gives an idea of this one. That is, let us consider the 5 d orbitals. Okay, this is the degenerate orbitals of the d orbitals for a free metal ion. Okay, now when the ligand approaches, these 5 d orbitals are raised to a certain energy level. Okay, so they are all raised to a certain energy level. If all the ligands, okay, and the d orbital have equal distance from each other, then the energy would be same for all the d orbitals. But since the orientations are different, and therefore if we consider for an octahedral complex, okay, this 5 d orbitals will split into this form, that is this way, where these are dx square minus y square and dz square. Okay, and this is of dxy, dyz and dzx orbitals. Okay, now this set of orbitals is called Eg. This set of orbitals is called T2g. Okay, Eg and T2g. This will be in the subscript. Okay, Eg and T2g. Okay, so Eg and T2g set of orbital. This is for an octahedral complex. Now, moving on to the next one, that is, see, the energy gap between these two set of orbitals, okay, that is Eg and T2g, that is called crystal field splitting energy, okay. And for octahedral, we represent or we denote it as delta O. If it is tetrahedral, we will be representing by delta T, okay. We just change the letter. Now, the next one is, let us try to study about this one, the energy gap, okay. That is, see, this is just in general, okay. I have considered for the octahedral complex, okay, octahedral complex. Now, here, if it is for octahedral complex, the energy gap, okay, will be of value 2 by 5 delta O, and this one will be 3 by 5 delta O. Okay, this is the energy. Okay, this is the energy for Eg and T2g set. Okay, now the next one will be, let's study about the octahedral complex, how we got this splitting of the d orbital, okay, where Eg is on top and T2g having lower energy compared to Eg. Okay, now in case of octahedral complex, there are 6 ligands. Okay, there are 6 ligands. Okay, now all these 6 ligands are present at all the corners of 3 axes. Okay, all the 6 ligands are present at the corners of all the 3 axes. Now we have the orbital, that is dx square minus y square dz square, okay, dxy dyz dzx. For any octahedral complex formation, the ligands will be approaching through all the 3 axes, isn't it? It will not approach between, okay, the ligands will not approach between the axes, but it will be directly through the axis, okay, through the 3 axes for the ligands. Now, along the 3 axes, okay, this dx square and dy square are present, okay, the orientation is exactly along each of the axes. But for dxy, dyz and dzx orbitals, they are present in between the 3 axes. Okay, therefore the approach of the ligand along the axis will be much closer. Okay, the distance between the ligand and the orbital which are present along the axis will be much closer compared to the orbitals that are present between the axis. Okay, and therefore the dx square minus y square and dz square, they will experience a greater energy, okay, or the repulsion will be more, and therefore they will be raised to a more higher energy level compared to this set of energy. Okay, that is for T2g, Eg. Okay, Eg. So that's why 2, 3, 4, 5. Okay, they are raised to a higher level like this. Okay, this is T2g set and this is Eg set. Okay, T2g. These are both in subscript. This is also in subscript. Okay, the energy gap will be, okay, the energy of this Eg set will be 3 by 5 delta 0, and this one will be 2 by 5 delta 0. Okay, this is how the energy of the d orbital is split in terms of, for octahedral complex. Now for tetrahedral complex, it will be just the opposite of this one. Okay, here in case of tetrahedral complex, okay, in case of tetrahedral complex, that is Okay, in case of tetrahedral complex, you see the ligands will be approaching in between the axes. Okay, therefore the ligands will be much more closer. Okay, the ligands will be much more closer towards the, in between the axis. Okay, rather than along the axis. Okay, therefore the energy will be experienced more, or like the T2G set of orbital will be raised to a higher energy level compared to that EG set of orbital. Okay, and therefore it will be just the opposite of this one, that is like this 3 4 5. Okay, this one like this. Okay, so T2G set, this is EG set. Okay, this is T2G set. The energy of this set will be 2 by 5 del T. Okay, for tetrahedral we represent it by T. This will be 3 by 5 del T. Okay, now the next one. Okay, like you see, for the crystal field splitting. Okay, for the crystal field splitting, that is the splitting of this d orbital depends upon the nature of the ligands. Okay, the nature of the ligands, that is, the stronger is the field of the ligand, the greater will be the splitting. Okay, the greater will be the splitting. So we have a series called the Spectrochemical Series, where the ligands are arranged in the increasing order, or in the increasing order of their crystal field splitting energy. Okay, so for example, iodine, bromine, okay, or iodide bromide, and so on. Okay, H2O and up to Cn. Okay, so iodide is a weak field ligand. Okay, cyanide is a strong field ligand. Okay, so a strong field ligand will split the d orbital to a much greater extent, okay, compared to a weak field ligand. Okay, now if this strong field ligand can, since it is strong field ligand, therefore it will split the d orbital to a much greater extent. Therefore, when we fill the electrons, since this one is a strong field ligand, therefore the electrons will be first filled in the EG or T2G level, okay, for tetrahedral and octahedral respectively. Okay, if the field is strong, since the ligand is a strong field ligand. Okay, but if it is a weak field ligand, then the energy gap will be less. Okay, therefore the electron filling will be singly filled in both the orbitals, although they are splitted, but the energy gap is less. Okay, therefore you will first singly fill all of the orbitals. Okay, because the gap is less compared to a strong field ligand. Okay, and therefore, that is how the weak field ligand and strong field ligand are differentiated. Okay, and therefore we come to know from there the magnetic properties, whether that particular complex will have a diamagnetic or paramagnetic properties. Okay, that is how we come to know. There is one more thing, that is regarding the high spin and low spin. Okay, so high spin means more number of unpaired electrons. Okay, high spin means more number of unpaired electrons, and low spin means less number of unpaired electrons. So for this one, since this one, a strong field ligand, since it split the d orbital to a much greater extent, therefore it will be a low spin. Low spin means less number of unpaired electron. Okay, less number of unpaired electron. High spin means more number of unpaired electron. Okay, so for a weak field ligand, since it will first fill all of the orbitals singly, therefore it will be low spin. okay, I mean high spin, yeah, for a weak field ligand, but for a strong field ligand it will be low spin, okay, which means less number of unpaired electrons. Let us see one of the example, okay. So here, based on the crystal field theory, we shall be discussing about the outer, okay, the involvement of the inner orbital or inner d orbital hybridization and outer d orbital hybridization, and also the magnetic properties, okay, whether it is diamagnetic or paramagnetic. So here we know that Cn is a strong field ligand and H2O is a weak field ligand from the spectrochemical series, okay. So moving on, next one, the iron atomic number is 26, therefore the outermost electronic configuration will be 3d6,4s2 for both of them. Oxidation state after calculation we got +3 and +3 for both of them, okay. Now for a free metal it will be this, okay, the electronic configuration, the outermost shell, okay. Now since the oxidation state is +3, therefore 3 electrons will be removed, okay. So this one is removed, and from here the paired electron is removed, therefore here singly filled, okay, only 5 electrons are left, isn't it? See, 6 + 2 is 8. From there if we remove 3 electrons, then only 5 electrons will be left. In the next step, for the formation of the complex, we know that Cn is a strong field ligand, therefore it will split the okay, d orbital into these two sets. Since it is octahedral, therefore it will be Eg and T2G, okay. Now the energy splitting will be in such a way that, okay, the electrons that are singly filled here, okay, will be available only in the T2G set, okay. So it will be, because of the energy gap is high, that's why the electrons will be filled here only. See, for this case, since H2O is a weak field ligand, okay, weak field ligand, therefore when the H2O approaches the metal, okay, it will be, see, the gap will be less, okay, therefore all the 5 electrons will be singly filled in all of them, okay. Now in the complex formation, the hybridization involved is, see, outer, isn't it, D2sp3, okay. So 1 2 3 4 5 6, so 6 D2sp3 or hybridized orbitals are formed, okay. And here it will be, see, sp3d2, isn't it, sp3d2, okay. So it will be sp3d2, so 6 sp3d2 hybridized orbitals will be formed, and that is how we come to know regarding the outer and inner orbital like involvement, okay, for the hybridization of the d orbital. So here both of them have unpaired electron, that's why the magnetic property is paramagnetic, okay, for both of them. So I hope you are clear with this one.